Okay. Now, I guess everybody should be able to recall the types of tests. You know, earlier on we talked about single well tests and multiple well tests. The build-up test is one of the major single well tests. The build-up test is actually made up of two periods. If you look at diagram if you look at the schematic, you would see that the build-up test is actually made up of a drawdown period and a build-up period. And always remember that whenever we write the idealized plots for any of the tests, they come as twins, the pressure plots and the rate plots. I believe you must recollect that. One of the major uses of the build-up tests is to determine average reservoir pressure, you know. But similar to what we did for the drawdown test, you can also get permeability, you can get skin, and some other properties. So there are two major plots or methods used for the analysis of build-up tests. And that's why you have the bottom. You have the Horner plot, and then you have the MDH plot. The Horner plots and the MDH plots. Those are the two major plots used for the analysis of build-up tests. They are not the only ones, but they are the two major plots for when it comes to conventional analysis. So I'd like you to take note of that. Now, recall that I'm actually going over what we've done before. In the two slides from now, I mentioned that the build-up test is actually made up of two flow periods. So you have a drawdown period, and then you have a shortening period. And that brings in the principle of superposition. So you can look at the build-up test as actually two flow periods, one where you have a finite rate Q, and one when you have a rate 0. You flow at a stabilized rate, and then for the other period, it's shorting. But we take the 0 as a rate in itself. And this slide actually exemplifies what I was referring to, where the build-up test is now a superposition of the flow period. It's assumed that the effects of perturbing the system due to production last for a total time of Tp. Tp is producing time, delta T is shorting time. And so this brings us to equation B1. Equation B1 is the equation for the analysis of a build-up test. And of course, if you look at it, you see that PWS is shorting pressure. It is directly proportional to the log of Tp plus delta T over delta T. So you could, on a semi-log plot, you should have a straight line. If you plot P shorting pressure against delta Tp delta T over delta T. So let me just ask you guys, under what conditions would there be a deviation from the straight line? What could lead to a deviation from the straight line? I like an answer from someone. What could lead to the deviation from the straight line? Okay, well burst storage, reservoir boundary effects. Okay, good. And also, so when you and also well bore damage skin. So that's good. Okay, so I have the responses which I was interested in. Great. Now, so you could be faced with, or a question could be presented to you where you are not given TP. Please hold a sec. Sorry, guys, I apologize. I had to pick the HOD's call. Now, so I was where I left up. I said you might be presented with the question where you are not supplied with producing time. Equation B2 comes in handy. Here, the producing time can be estimated from NP, which is cumulative production, and Q naught, which is the rate. So remember that for the build-up data, or for the analysis of the build-up data, what we are presented is the shorting pressure being proportional to the ratio of Tp plus delta T over delta T. Tp plus delta T over delta T is referred to as Horner's time, and that is what is plotted. And of course, equation B3 here is how, take note also in equation B1 that the skin factor is missing from this equation, unlike for the drawdown case. So equation B3 is used to calculate skin in this case. Now, okay, I think it's a good time to mention that I provide equations for this course in the exams. I hope that is clear. I provide equations. So
yes, sir.
The idea is that you should have practiced. Oh, okay. Adenuga, I can see your hand. You can speak. Adenuga, unmute yourself and speak. Yeah. Adenuga, your hand was raised. Is it there?
Hello.
Yeah. Okay. Probably when he's ready. Okay, your question has been answered. Okay, fair enough. Great. So let me go back to. Okay, so please, there's someone in the background speaking. Just unmute yourself. Okay.
Please, Zola Dimeji, mute your mic.
Please mute your, yeah. Thank you. Now, if you take a look at this slide, for my own, this is 269. So this is, of course, you will see a clearer one later, but I'm showing you this to point out a few things. Now, so this is a typical plot of your build-up test data on a semi-log plot. If you notice, you see that this is 10 raised to the power 4, 10 raised to the power 3, and I think we went through how to use the semi-log plots. Of course, your shorting pressure is plotted on your y-axis. Now, if you take a look at this plot, the lower x-axis, you have Horner's time plotted. That's Tp plus delta T over delta T. On the top, you actually have shorting time plotted. I will come back to the issue of shorting time. But for now, I'm dealing with the Horner's time. So some key, of course, you will note that prior to P1, this is where, okay, so I can take this. So all the points before P1 that I've highlighted here are off the straight line. And this just tells you that these points are affected by Well-Boy effects. On to, and then here, this is also a deviation from the straight line, and this is due to reservoir boundaries. However, typically you would use points on the straight line. The straight line is what is your infinite acting radial flow. So please take note of that. So I think I will okay, one other point that I've not talked about is this Tp plus 1 over 1. So this is how to get PWS at 1 hour. Remember that delta T is shorting time. So if you want to get the PWS at 1 hour, in Horner's time, it translates to TP plus 1 rather. That's TP plus 1 over 1. Okay, I'll show you this, so let me not spend too much time on this slide. I hope you can follow me so far. So this is okay. So this is a typical question, and I think this was also one of the questions on the tutorial. Okay. Okay, I saw Caleb highlighting something there. So if you look at the table, you have, okay, probably I should exit slideshow. Good.
Excuse me, sir.
Yeah.
Sorry, can I ask a question?
Yes, you can.
Please, can we get the, I noticed you're recording it. Can we get the recorded this thing?
Yes,
after
you
the
can.
classes?
Yes, you can.
Okay. All right. Thank you.
I'll try to make it available. Okay, so I've come out of slideshow mode. If you look at this, you have delta t to the left, Tp plus delta t. Remember that Tp is either given or you calculate it from that 24 times Np over Q naught. Here, the division sign is missing here. So this should be into brackets Tp plus delta t over delta t. And this is shorting pressure. This is given. So the 2761 is the pressure. That's the first shorting pressure. This is the pressure just when the well is shorting. And this, you notice that there's a buildup of the pressures. So this is a typical question where you are expected to calculate average permeability, skin factor, and pressure due to additional pressure due to skin. So the very first thing is to plot the points on a semi-log graph. Note, this is the log scale. It's just that in this plot, the grid lines are not showing. And similar to what you have earlier on, you have departure from the straight line due to well-bore effects, and then this is the straight line period. This is the straight line portion of your test. Note that this straight line is due to infinite acting radial flow. So this is not due to pseudo steady state effects. This is there. So please take note of that.
Just now. My class is this class. I did class.
Please, mute your mic.
Excuse me, sir. Sir.
Sorry, guys, I had one of my colleagues knock my door. Okay. So.
Sorry, sir. I want to ask you.
Sorry?
Sorry, sir. What were you saying about the pseudo steady state on the graph?
Okay, so now, yeah, I think this is also a very important point. Now, straight lines mean different things depending on the graph you are on. So note that I'm on slide 271 here. Let me go back. Let me just address the issue of the straight line. Now, this is my own slide 244, and this is the drawdown plot. So for the person who was asking me, know that this is a semi-log plot, isn't it? This is a semi-log plot. Now, on the semi-log plot, you should have a straight line for transient flow, what I actually call infinite acting radial flow. Infinite. Remember the diffusivity equation and what we came out with, the solution to the diffusivity equation we discussed. So this straight line is actually referring to infinite acting radial flow, which loosely is transient flow. But it's transient flow after well-bore effects have been overcome. I hope you're following me so far.
No, sir. Sir, I don't understand something, sir. Like,
yeah,
just come again slowly, sir.
No, what exactly is your question? So that I understand. Okay, maybe the next thing I'll show you might explain better. So take a look at this plot. This is, I was the one who charted this. So this is a semi-log plot. On the semi-log plot, the straight line portion refers to infinite acting radial flow. I don't mind you saying it after me. Infinite acting radial flow. So the next question is, what is infinite acting radial flow? Isn't it? Great. Now, hold the thought, and now, ladies and gents, take a look at this plot. This is figure D3. What type of plot is this? This is a regular Cartesian plot, isn't it? This is your regular XY plot, a regular Cartesian plot. Am I communicating, people?
Yes, sir.
Yes, sir. Yes,
I
sir.
hope I am. I hope I
Yes,
am.
sir.
Okay. I just came out of that to ensure. Okay. Now, so if you take a look at, so this is a Cartesian plot. Now, interestingly, on the Cartesian plot, this straight line portion is referring to pseudo-steady state flow. Remember that the equation for pseudo-steady state flow is the P dt is what? Constant, isn't it? The P dt is constant for pseudo-steady state flow. So the portion before the straight line, actually in this case, is transient flow. It's a combination of your transient flow combined with well-bore effects, and then your infinite acting radial flow. I hope I'm clear so far.
Yes, sir.
Okay. Because of your question,
Sorry, sir. Hello,
yeah,
sir.
I'm with you.
So on the Cartesian plane, are you seeing the straight line is the pseudo-steady state region?
You didn't see the straight line. I didn't get your
So
question.
like on the straight line Cartesian plot,
Yes.
I'm trying to understand what you said.
Okay, so
Are
now
you the
listen.
straight line on the Cartesian
No,
plot?
so let me
Pseudo-steady state?
Idris, just listen for a moment. Now take note of this. We on whether is the semi-log plot or the Cartesian plot, we are on those plots, all the test points are there. What comes out as whether it's straight or curved is a function of what is plotted. So here, now, okay, since this is an important point, and I don't want to lose you guys here, so permit me to let me backtrack a bit. It might be challenging for me, but let me come back here. So, ladies and gents, sorry, it appears I'm going back and forth, but this is important. Now, let's go back to what everybody is familiar with. For transient flow, the partial derivative of pressure with time, with respect to time, is a function of both position and time, isn't it?
Yes.
For pseudo-steady state, the partial derivative of pressure with respect to time is constant. So this is actually not really a partial derivative. This is the P dt is constant. And this tells you that on a regular Cartesian plot, if you plot pressure against time, you will have a straight line. Now, if you have a straight line, it means the portion for which you have a straight line is pseudo-steady state. Now, on a Cartesian plot, if you have no slope, you're having a flat profile. Note, on a Cartesian plot, that is steady state flow because there's no change as pressure with time. Now, coming back here, most of our analysis in this course is in the transient flow region. Note that full radial flow is first preceded by interference or well-bore effects. And this brings me, so I hope you've been able to follow the discourse so far. Okay, I just wanted to check that if I have, wait, I think I'm fine so far. Now, so let me make my way back to where I was before I try to address the questions. Now, so the question, I think, Idris.
Yes, sir.
Have I addressed your question?
Yeah. Okay, thank you. Yes, sir.
Now, so for what we have done so far, because next week, I'm going to introduce a different type of plot. We've dealt with two major plots. We've dealt with the semi-log graph, where on the y-axis is the regular Cartesian scale, and on the x-axis, the time axis, it's a log scale. And that's what you have here. On the semi-log graph, the straight line portion, which is the middle time here, is what we refer to as infinite acting radial flow. It means that it is transient flow unaffected by well-bore effects. During this period, even though the straight line here is simply a mathematical thing. It's a mathematical thing because you can because the log approximation to the EI function affords you this opportunity. So because for some period of the log, based on that log approximation, we can analyze whether it's drawdown test or build-up test using the semi-log graph. So that said, permit me to go back to. So I hope I have made those points clear. So any questions so far? Is everybody with me? If you have any specific question, please, you can raise it at this time. Okay. So I'll take it that you guys are. So let's go back to this question.
Sorry, sir. Sorry, just to be clear. So on the Cartesian plot, the straight line is studio steady state, while the curve part is the transient part.
Why exactly? Why the curve part is transient flow? Exactly. That is very true. Great. So let's look at this example. And so what I was referring to, so what you will be, now take note, what you will be given, maybe under test conditions, exam conditions, is your time, your shorting time, and your shorting pressure. These two columns are not typically provided for you. So, but to simplify your analysis, what you do is when you are given, okay, so Joseph, you can ask your question. Cruz, you can ask your question.
Regarding the explanation you gave on the Cartesian plot, you stated diffusivity is constant for steady, and for steady diffusivity is 0, for diffusivity changing. Like if we are to go by that for a graph, I think it only applies to just the pseudo steady aspect, because for the well-bore storage, for the transient region and the well-bore storage region, like which equation are they following for the well-bore storage and the transient region? But I didn't get for the steady state, the equation you stated, I got that, but for the well-bore.
Okay, so.
Sir, we did not get the question. Cruz, we can't hear you.
Yeah, Cruz wasn't quite clear. No.
Can you guys hear me?
Okay.
Can you guys hear me well?
Yeah, Cruz, yeah, go ahead.
I'm saying for the equation that like the equation the first two regions are like are following. Like I wasn't really clear on that, but I was clear on the one you explained for the pseudo study.
Okay, so you are clear about the Cartesian plot, isn't it? Cruz.
Cruz, can you just type out your question? Maybe it'll be better.
Okay, yeah, good thing. Please type out your question so that probably in wrapping up I can address it. Okay, it's okay. You got Cruz. Okay, fine. But ladies and gents, just try to follow me going forward. At least this is one of the questions, so it would be helpful for you to be able to get this. So what I was mentioning, Cruz, hold the thoughts. I would probably wrap up with what I'll reiterate when I'm done. So in whether it's exam, test, or even real life, what you are given, you'll be given your shorting times. That's the first column to my left, and then you'll be given shorting pressures, the column to my right. Now, we call equation B1 equation. So, and probably this could also help Cruz. Look at equation B1 again. In equation B1, your shorting pressure is directly proportional to the log of the Horner's time. That means if you plot your shorting pressure against your Horner's time, it will give you a straight line on the semi-log plot, provided those time periods are an infinite acting radial flow. So going by this, here you try to produce the Horner's time. So the first thing you do is you add TP is a constant. So you add TP to each shorting time. That gives you the second column. Then you now find the ratio of TP plus shorting time over shorting time. And that is what you have in the third column. Let me continue. If you do that, the next thing would be to go to take to make the plot on the semi-log graph. My counsel is that you need to leave some clearance. Don't use, if you look at the table, the highest pressure here is 3323. The highest pressure is 3323. But if you look at my plot, my highest pressure here is 3350. The reason, and you see why, you need to leave some clearance above your plot because of the need to extrapolate your points, to extrapolate the straight line for extrapolation. So please take note of that. The lower is a matter of convenience. You see that the lowest, now take note, the shorting pressure at shorting time of 0 will not come up on your plot. This 2763, this force pressure is not going to come up on your plot. So you are starting with the 3057. You look at it, and that is what coincides with the point here. So the next thing, remember, when we use the semi-log plot, we do not go and find the log. We don't go to find the log of the, we don't go to find the log of the time period anymore. Thank you. You don't go ahead to find the log again. You're plotting the time directly on the semi-log plot. So let's take it. Let's take the second rule, for example. Your time is 0.1, but note you are plotting the Horner's time, which is 3101. So what you are doing is you are plotting 3101 on the x-axis, and then you are plotting 3057 on the y-axis. So if you look at this, remember that the log scale is in cycles. For when you are using the Horner's time, so that it gives the semblance of a build-up, the scale is, you see, it's going from the highest to the lowest. It's going from the highest to the lowest. It's a thing of convenience. If you did it the other way around, it would look like a build-up. It would look like a drawdown plot. Even though you get your analysis, you get the same results. So this is a thing of convenience to give you the feel of a build-up. And you look at this. This is, so for each cycle, this is 10 raised to the power 1. This is 0.1. No, this is 10 raised to the power 1. Rather, this is 10. This is 100. This is 1,000 on. The point we are looking out for is 3101. That falls in between 1,000 and 10,000. So this is 1,000. This is 2,000, 3,000, 4,000. So you know it's 3,101. And that's why the plot is here. So the next thing, this is not the best plot to explain this, but let me see. Okay, probably when I get to the second example. So first of all, you need to be able to put the test points on the semi-log graph. Secondly is how you pick up the slope. I'll use the second example to describe that, because that one has the grid lines. So let me erase so that I can go to the second example. Here I'm assuming that you know what to do. Note that the slope for this graph is usually in PSI per log cycle. PSI per log cycle, that is the units. In this case, it's 40. I'm not demonstrating that, but when I go to example 2, I'll do that. And of course, from the formula for getting permeability is the same whether it's build up or drawdown. Now, we are also required to get P at 1 hour. Note, P 1 hour is delta T is equal to 1 hour. Delta T is equal to 1 hour. But you need to find the equivalent Horner's time. So for the Horner's plot, you need to, delta T is 1. So it's going to be TP plus 1 over 1. So it's actually TP at plus 1. And that's how you get this. This is applying the skin formula. Take note, this is the modulus, the absolute value of the slope. This is the flowing pressure when we're shorting. That's the first pressure point on that table, and the rest comes to substitution. This is just application of formulas. So before I go to example 2, let me just be sure whether to see whether I have any reaction. Okay, please, sir, can you come again on this particular point of plotting? What parameters are and how on the log plot? Fine. So Adedamola, I will address your question in example 2. So please be attentive. I'm going to do that now. So let me share my slides again. Great. Now, so let's look at this example 2. The analysis of the build-up pressure test showed that an oil well with a productivity problem. Prior to shutting in the well, the following bottom mode pressure at the time of shutting was 2,309 psi, and the well produced oil at a constant rate of 100 Stockton barrels per day, using the following data. That's well bore radius, formation volume factor, the thickness of the oil column, viscosity, compressibility factor, porosity. Here we are given producing time, which is 310 hours. Estimate the following: the slope of the graph, in this case, is the slope of the semi-log graph, the effective permeability to oil, skin factor, altered zone permeability, effective well bore radius, additional pressure drop. So guys, you can now try to follow me here. Okay, unfortunately, in this case, I think I have the data for this. Let me see if I can do that. So what's this? 3, because in the material I didn't provide the table for this, but let me see. I think I have it somewhere. So please just give me a little. Let me dig that out. So just hold on. I want to get the data on the basis of which that graph was produced, so that I can explain. Yes, I have seen it. Wait. Build up Okay, so I will share my screen again. So Adedamola and they all, please follow. Now, this is the data. It's not in the slide, but this is the data. So the data you will be given typically is the shortening time. That's delta T. And then the corresponding shortening pressure. This is actually the last pressure that was recorded just before the well was shortened. So that is PWF at delta T is equal to 0. And these are corresponding shortening times, corresponding shortening pressures. So what you're trying to do is to get, for each shortening time, that's for each delta T, what's the corresponding Horner time? So Horner time is Tp plus delta T, all in bracket, divided by delta T. And if you look at this, okay, I haven't calculated it, but I think this. So I think the question said that the Horner's, what's TP? TP is 310. Okay, so I can calculate it on my sheet. So here, TP is 310. Let's put the bracket so that we don't mess it up. TP is 310 plus, this is the shortening time, close the bracket, divided by the shortening time. Wait, and be sure I'm doing the same thing. Forgive me, let me just be sure that I'm dealing with the same problem here. Written, okay. So this is what it should be. 310, which is TP. This is your delta T, and this is your delta T. So this is your Horner time. That probably is an error for me. And you do the same thing all through. So what you're trying to do is remember that TP is constant, and then you add your shortening time to it, and then you divide by your shortening time. This produces the Horner time. Now, what you now want to do is to plot your shortening pressure against the Horner time. Remember what I said, the first row is not going to be included on your plot. First of all, because on the semi-log graph, you don't have any zeros. And then this plot will take your, if you add this pressure plot, it will take your graph out of scale. So what we are doing now is to plot this on the x-axis and this on the y-axis. So if I come back here, So I'll need to check. Okay. So just for so that it tallies with what I had before, I think the difference is in this question, this is actually a shorting, a TP of 72. So I think I'll correct that. This should be 72. So I'll update the slides and let you have them. This should be a TP of 72. And I think that will correspond with what I've been doing so far. This 310 was taken from the last question. So guys, I've corrected this. I'll let you know on example 2. The TP actually should have been 72 hours. So this is my error. And it's good I'm solving it now. So TP here is 72. And if you follow how I explained, you will get this as your corner time, and then you will get this you are given. So remember, you are given the shorting time in the question, and you are given the shorting pressure. I hope I have not lost anybody.
No, sir.
Okay. So first column is time, second column is Honors time. So in the where are there 2 Honors times? Okay. Okay, good question. Now, so note this, I already had this on my sheet. I'm only doing this for explanation purposes. If we followed what I had in the previous slide, this is what it was actually we had 4 columns. You know, we had TP plus delta T. And if that was going to be the case, that would have been TP, which is 72, plus the delta T here. So what I've just done in this case is I've combined the third and the second and the third columns, which gives us the Honor time. So you see that this now looks like what I did in example 1. So now let's go to the second part, which has to do with plotting, putting this on the semi-log plots. So take note, this is the plot below. So let's take this one that has 8. So note that the shorting time is 8, but what they are plotting in this case is the Honor time. And the Honor time is 10. This is a perfect one. So in this case, this is where it is. For this question, you only have 2 cycles, 1 to 10, 10 to 100. And then that's a Honor's time of 10. And then the pressure is 2890. And you can easily get that from there. Let's take another point. Let's take 24 and 2915. So if you take 24, so this is 10, this is 20. Question 24. No, so this is 24 delta T, but remember it's the Honor's time we are plotting. The corresponding Honor time is 4. So it's 4 that goes into the graph. So you have 4. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But this is not 11. This is 20, 30, 40, 50, all up to 100. So if you go, this is 1, 2, 3, 4, and this is 2915. So the next thing is, how do you get the slope? And what I'm explaining here holds for whether it is draw down or build up. Now, to get the slope, remember that the unit for the slope is log per cycle. Log per cycle. So what you do is you need to take one cycle, either 1 and 10 or 10 and 100. Then you pick What is the pressure at 1? Here, the pressure at 1 lies at 2950. What is the pressure at 10? Here, it lies at 2890. So this is 2890. The difference between these two pressures, 60. So the slope of this graph is 60 psi per log cycle. Let me go over it again. And let me use a different log cycle here. If I was using here, I need to come here. Here, this is 2890. But here, you stick on the straight line, and this takes you to about 2830. So you find the difference between 2890 and 2830. That gives you a slope of 60 psi per log cycle. That said, I can go back to my material. Any questions before I move from here? Let me stop sharing my screen. So any question? Okay, let me check what they have.
So I'll come again with the slope. Can you come again with the slope, please?
The slope.
Okay, the slope. So second on that.
Yes, sir.
Okay, yeah, thank you. That the 310 was a mistake. 772, yeah. So let me come again with the slope. Let me come again.
And sir, I want to ask, we can randomly pick any of the points, or is there a basis for picking it?
Now, you see, remember, the slope is psi per log cycle. If you are going to pick 1, so if you pick 2 here, you have to pick 20 here, but it's you remember that it's very unsafe. The log cycle is not graduated equally. The log cycle is not graduated equally. The log cycle, you see that it kind of thins out. Right? You go from, as I'm going from 1 to 10, you see that the spacing between the lines gets smaller. So you can't just pick, you can't pick so pick at each full log. That's maybe at 1. You know, log 1 is log 10 to base 10. This is log. So the idea is you are picking at the beginning of a log cycle. So I don't advise you picking them randomly. No, pick at 1, 10, 100, 1,000. Pick at 10, 1, 0.1, 0.01, 0.001.
Sir, can you hear me?
Yes, I can.
Okay, very well. Okay. Regarding the units you said for the slope, psi per log cycle.
Yes.
Can you hear me, sir?
Yes, I can.
So
Go ahead.
I think the log has already been executed already as a result of the graph.
Yes.
So we should be having psi per cycle.
Now, whether I say cycle or log cycle, the idea is to give to send the impression home that your slope is not just psi. If you say cycle, it's a log cycle actually. I hope you understand. The cycle is a log cycle. It's not a random cycle. It's a log cycle. But you are right that what the semi-log graph does is to produce the log of the time for you. So you don't need to go to your calculator to do that. So I agree with you, it's a cycle, but it is a logarithmic cycle. So that's my response to that. Are we clear with this now?
Sorry, sir. This semi-log data plots is this something that we're supposed to like construct for ourselves?
Okay, I can.
Like,
okay, so I would send electronic copies to Gozi.
All right, thank you, sir.
I'll send some electronic copy. So if you can decide to print it or you want to, it's a thing that you can actually do yourself. But I'll send copies. So if you look at this is in Excel. This is a this is not okay. This is better. So look at this. This is a 5-cycle semi-log graph. 1 cycle, 2, 3, 4, 5. So I can go from 1 to 10 to 100 to 1,000 to 10,000 to 100,000. I could start from 0.001 and go that way. So I believe that I want to believe I've done like his way, of course. Yeah. So if you do Excel, all you just need to do is to transform your scale to a logarithmic scale, and it does it for you. It's way easier doing using Excel. So you can see Bright and the big guys for how to do it in Excel, but it's very straightforward. Because of time constraints, I won't go into that. Yeah.
Regarding the slope,
okay.
Regarding the slope, do you expect everybody to have the same slope? Because the points I'm seeing now, there are some I'm not seeing like it should be part of the.
You are correct. You are correct, Abdullah. You are very correct. So, in fact, I was doing a question. I was doing even one of my examples, one of the book text examples, and in the book it's 40 psi. When I did it rigorously, I came out with 48. I mean, rigorously means I did it. I extracted points and did that. So usually what I do is either I say you round up to the nearest 10, or I give some tolerance. For instance, let's say the answer is 68 psi per cycle, and you come up with a 70 or a 65. I use my discretion and I know but if you get an 80, for instance, I know you're way off. Not to talk of if you are giving me 200 and 250. So Abdullah, you are right.
Yes, sir.
We are not, except we are using a software for analysis. Except we are using it's automated, we are not going to get the same thing. We are not likely to get the same thing. So that you're right about that.
Sorry, sir. Can I see the graph again?
Okay, you can.
Sorry, sir. Regarding the software,
sorry, sir,
I'm actually speaking about that.
Okay, so software. Actually, I was very positive that your set would be the first that will be using the well-test analysis software. Actually, I'm in the process of making requests. Is going through the usual university channels, So, but unfortunately, you guys will not be able to use it. But hopefully, the next set after you'll be able to use the software for the analysis. Okay.
Okay. Sorry, I have a question concerning the graph. You said for pressure buildup, it is good to start from for the x-axis when we are talking about the honors time. It is good to start from the lowest, then like that. So, which means if you are to plot for pressure drawdown, it will be the opposite, right?
Okay, so exactly. Okay, David, you are right. I hopefully before my time runs out, I will show you something else. Remember when I started the talk on build-up, I said there are two methods. There's the Honor plot, and then there's the MDH plot, if you remember.
Yes, sir. Yes, sir.
So before I'm done, I will get to the MDH plot, most definitely.
All right.
You can see the difference between the two.
All right.
I don't know whether it was Wura or Cody who told me to show the plot again. So this is it. Basically, I think what is left from here would be practice. You might need to go back. I think I don't remember what I gave, 1 or 2 of the build-up problems in that tutorial set 1. So you might need to go over what you submitted, you know, after what I've mentioned now. But let me go back to my slides, you know, so that.
All right, sir. Please, I have a question.
Okay, what is it?
So I noticed that all the questions you tried explaining, they had graphs. Perhaps in exam, are we going to be asked to plot any graph to extract, like to be able to calculate the different parameters that we would need to complete our problems that we're trying to solve?
Okay, is that Vivian?
Yes.
Okay, nice talking with you. So, perfect. Under exam conditions, you'll be required to plot a graph. And I can tell you for free, based on my grading system, that graph alone used to be, on a question of 20 marks, that graph alone is 5 marks. You know, because you can't evaluate anything if your slope is wrong. And you quite agree with me, isn't it? So whether we even use the LMS thing or whatever, you would need to have the graph. You will need to plot. So I don't, in my questions, whether both for the build up and the drawdown, you'll be required to make a plot. Except I just feel magnanimous and I don't usually feel that way during the exams.
But considering we're going to be having an online exam,
yeah,
are we going to be plotting? Are we going to be plotting online or
no? What for the if we would do it online, what all I require from you is the slope.
Okay, now I am very confused.
So won't have to submit the plot.
I think it's trying to say that.
Now, so okay, hold on. So Vivian and the guys, just hold on. Now, I haven't concluded on what I'm going to do. So on the LMS, there are different options, but the two major ones that tend to concern us is you could submit. I could ask you to upload, submit your answers like a file. Probably I can even allow you to use Excel, for instance, and you upload your submissions as a file, which I download and I now grade. Or you do it, that's one way of going around it. The second,
sorry, is that still under exam condition?
God bless you. Okay, Vivian, can we let's leave exam issues out because it's getting to my head too.
All right, so I have another question.
Okay, go to your second question.
So this question is, okay, let me just go ahead. So you've already taught us about this build-up test and everything, but I feel like if we don't know the applications of all these things in the industry, trust me, after this semester, a lot of us will forget about it.
Word.
Because this this slides you gave us, basically a lot of us had to start reading from the beginning because we already spent home doing different things that were not school related.
Okay.
So it's like we're trying to finish up a whole semester within 5 weeks.
Yes.
That was why everyone seemed to be complaining about the slides, that they were a lot. Because we are basically starting from the beginning. So for us to be able to remember, we need to at least have an idea on how all these things are being applied, so that even if we try to forget tomorrow, we'll be like, oh, this is where it's applied, and something like that.
Okay. This your question kind of takes me aback, but I will I will answer it in a bit. I'll answer. Cruz, your hand is raised. Can I? Let me take your question too.
Sir, I'm going through the sir, can you hear me?
Yes, I can.
I'm going through the questions you gave us during the break.
Yeah.
During the break. So on the ninth question, I can see my graph. So I noticed that my graph is not showing me this thing. You know, we have straight line and the curved section.
Yeah, yeah.
But some graphs don't give that. Some graphs just a straight line, and
so it's just a straight line. Okay.
So is it an anomaly or
no? You see,
apples.
You see, so okay, so let me address your question and Vivian's question because it's very important. So stay with me. Let me bring something up. Let me stop sharing, and then let me seek to address the concern of relevance to the industry. So just give me give me a short while. I will.
Can I quickly ask a question?
Yes, you can.
So you said that this is a build-up test, and that's why the values went from 100 to 10 and downwards. So if it's a drawdown test, it will go the other way, right?
No. Wura, let me correct that. For the Horner time, for the Horner plot, that TP over delta T. You see, delta T is increasing, but TP plus delta T over delta T is decreasing. Did you see that?
Yes, sir.
So to give the graph the appearance of a build-up plot, the axis is taken from the highest to the lowest. Just stay with me. What I'm going to use to end this class would give you a better idea of what I'm talking about.
So I'm guessing it's just for appearance sake, it doesn't affect just appearance sake.
Yes, it's for appearance sake. It is for appearance sake. Okay, so sorry, I've been looking for an appropriate test report I can share. I never expected that question, but okay, I think I've seen something now. Okay, so let me share my screen. So, Vivian, are you there?
Yes, sir.
Great. Can you see my screen?
Yes, sir.
Good. Now, so what I have here projected is a well test analysis report from well 25 ST, that is short string. The reservoir is E1X. The field is Utorogu. Utorogu is in the Western Niger Delta. That should be Delta State to be precise. And of course, you can see the operator there. I'm showing you because of your question. So this is a well test analysis report. And of course, let's forget about document numbers, authorization, and all that. So I would run through. So this gives the background of the field. Now look at the test objectives. The test objectives were to prove productivity from the reservoir and determine technical potential, to obtain surface samples of the reservoir fluids for PVT analysis. Look at point 3, to determine reservoir and well properties, reservoir permeability, initial reservoir pressure, formation KH, that's the permeability thickness product, reservoir boundaries, and skin. And what's for? To determine effective drainage radius in support of proved reserved ratings. Now, so.
Sorry, sir.
Yes.
Please, can you go back to the objective? They said in summary, yes. However, due to
the short duration of the build-up period, the last two objectives as stated above could not be fully met as reservoir boundaries were not detected from the test. What this means is that if they plot and we'll look at it way below, if you plot this, for instance, on a semi-log plot, the departure from the straight line at the end of the plot will not be seen. All the points would line up on a straight line, should line up on a straight line, apart from the early points, which would be distorted due to Wellbore effects. So this is referring to choke size on which the well was flown. This is for deliverability testing. And let me go to, so here, these are some specifics which are inputs into your well test analysis. This is an IPR plot, inflow performance relationships, because this is actually a gas well. And this is IPR VLP. This is interesting. I'm bringing this up. Now, if you now look at this, so look at the figure 4. Guys, I hope you are following me, because we are talking about relevance to the industry. Now, if you look at the figure 4, which is not too clear because it's against the background, you see you have pressure, and then you have pressure difference. And this actually follows, it looks a little like one of the plots I showed you during DST, even though it's exaggerated. But this is pressure, and on the x-axis is time. It's shown QAQC plot showing pressure differential between 2 gauges. Now, look at figure 5. Figure 5 is rates and pressure profiles synchronization. You would see that you are having pressure, a pressure plot above, and then below is a rate plot, which seems to be in stepwise fashion. So what they were doing, they were producing the well. So they said synchronization of flow and build-up periods. So here, where you have these steps is where you had the flow periods, and here is where you had the build-up period. I hope you guys are following me. At least I hope you can appreciate what I'm trying to do. Now, going forward, you have a number of things which we are yet to discuss. This should be my last lecture. This is, figure 7 is the log-log diagnostic plot. Remember that what we have done is the semi-log, but this is the log-log. I'll be ending the class with the log-log. So I would leave it at that for now. Now, take a look at this figure 8. Figure 8 is the semi-log plot for the build-up test. And of course, this is actually gotten, all these are snapshots from the software. So you see, for here, they used conventional well test analysis was applied to analyze the pressure time response of the build-up period using Sapphire. This is one of the well test software. The log and the 7-log plot of the pressure response was matched to models based on the available information of this and this. So the reservoir model, so you will see that these are results of the build-up analysis. So the big question is this now. If you look at this plot and you look at the red line, the big question is what do these portions, the different portions of this graph, what do they stand for? So without, even though I've not read through the report, here, where I'm encycling, this is infinite acting radial flow. Here are portions where your test is affected by Wellbore effects. And this is analysis, that's build-up data, and this is analysis of flowing data. So I hope I've been, so what are we trying to, so this takes me back. So Vivian, I'm directing this question to you.
Yes, sir.
What is well testing?
Okay, sir. I'm going to answer your question. Well testing, perhaps the process of either producing or injecting into the well in order to into the reservoir or well, basically, to measure the pressure and rate under controlled conditions.
Thank you. That's a good definition. So the next question is, why are you measuring pressure and rates? You are measuring pressure and rates to infer some properties of the reservoir. Under formation evaluation, where you use core analysis, you take core samples or you take well logs. Those ones are where they are indirect measurement. But now, this is a dynamic method through either by flowing or shortening the well, you can infer some things about your reservoir. Have I been able to convince you about the relevance of what I've been teaching you?
Yes. Thank you.
I hope so. Anyway, this our class was built for, but I hope guys you've been able to appreciate what I've been trying to do. What I think is a major gap is the fact that probably we didn't get on well test analysis software. Somebody, oh my, you guys are clowns. Somebody says Buddha is sleeping. Okay, yeah, that was clowns. Now, so let me bring my lecture to a head, but I hope you guys have been able to appreciate this in the small measure that I've presented. So let me try to bring the lecture to a head. I didn't intend to go into a number of things which I did, but so let's at least finish the build-up. Let's finish the build-up problem. So remember that we have put the test plot, and of course, in the industry, nobody will be punishing you like Dr. Lamigo, okay, to put this on envelope paper. No, you'll be doing the analysis with software, but it's just good for us to know the basis for analysis. So now we have, we put the test points on the graph. We have determined the slope. We have determined our slope. So the next thing is to be able to infer properties. Oh, we have raised hands, okay? Let me address the raised hands. At least I know where I'm going to end today. Vivian, have I addressed your concerns? I think your hand is still raised.
Yes, sir. Sorry, I put it down now.
Okay, great. Okay, so let me go back to share my screen. So basically what is left is to be able to apply the formulas, So here I wouldn't belabor that. Yes, so this is actually where I was supposed to start the lecture. Now, everything or most of what I've discussed so far entails using the Horner time. And let me show you Horner time one more. Let me flash the Horner time again so that all what we've been doing. Remember that as your shorting time increases, your Horner's time reduces. And that's why for our parents, as Cruz rightly mentioned, the scale is more like from the highest to the lowest for the Horner's time. When I started the lecture of today, if I recollect, I mentioned that there are two conventional methods, which is the Horner plot and then the MDH. So let's end with the MDH method. And that will probably take us to where I was supposed to start today's lecture. But now, the Horner plot may be simplified if the well has been producing long enough to reach pseudo-steady state. So remember that when I started, I mentioned that the build-up test is actually a superposition of two flow periods, a flowing period and then the shorting period. Now, if the well had been if we can make that assumption that the well has produced long enough to reach pseudo-steady state, that implies that Tp is much greater than delta T. Now, if Tp is much greater than delta T, we can assume, or we can take it that Tp plus delta T is approximately equal to Tp. And let's put some numbers to it so that we can flesh it up. Let's say to get to pseudo-steady state, we needed to flow the well for about 2,000 hours. And let's say our shorting period doesn't exist. It doesn't go beyond like 20 hours. So we can say that 2020 is almost equivalent to 2000. So if we can sufficiently say or assume that the well has produced to reach the steady state, the Horner's time can be simplified to Tp over delta T. And using your logarithm rules, log Tp over delta T is equal to log Tp minus log delta T. Please, there's someone who is on the road or something that needs to mute their mic. Now, remember, Tp is off your mic. So log Tp is a constant. And that brings you, so we can now simplify that equation B1 to this. So the equation now becomes delta P, shorting pressure is now equal to P minus M, which is the slope, into log Tp minus, and remember this is a constant. So in this case, we can plot shorting pressure against shorting time. You remember that what we did initially was shorting pressure against Horner time. And this takes us to remember what I mentioned. So if you look at this plot now, you have, this is shorting time. And you see that it looks very much like the plot we did before. The only difference is this is regular. So here, the scale is increasing as it ought to. Scale is increasing. And then you do the analysis in a similar manner. But remember what the assumption is. You flowed the well sufficiently to reach pseudo-steady state. And this takes us to, so this is the second analysis method for using, and interestingly, if you plot it, you get similar slopes. May not be quite the same, but get similar slopes. The properties you get will not be too far away, provided the well has been flowed long enough for us to make that assumption that TP plus delta T is as good as using TP alone. And this actually takes us to determination of average reservoir pressure, where I was supposed to start my lecture for the day. I hope it has been a fruitful lecture. So let me just take questions and I'll make my final remarks. So any more questions? Any questions for me?
So I have two questions.
Yes, Cruz.
Although my first question, like I'm actually in talks with Idris now about the first question I asked regarding why we had like a straight line.
Okay.
Mushiri said it was an ideal situation. My second question has to do with the graph for the, I think there was a time you were showing us a graph of the honor time and the time itself.
Yeah, you're right.
Oh, I don't think you didn't mention the interpretation of the time, like how the time and the pressure graph is supposed to look like, provided we are not using the
okay. So
honor.
look at this. I think this is so this is actually a graph where you have both the honors time, both the honor time and your shorting time plotted. Here to the lower x-axis is the honor time, and here is the shorting time. The only thing, and I don't really advise you to do this, is because the scales will be a little shifted. The log scale here doesn't align with the log scale here. So except probably you are using some software, you might not quite get that right. So for when you do the MDH plots, you plot what do you call it? Shorting time direct. You're not doing any conversion to honor time. You know, we had to do a conversion of shorting time to honor time. So for this one, you just plot the shorting time directly. And then you use that in your analysis. So based on, usually when we do analysis, the first thing is to get the plot. So you put the plot will look very similar to if you use the honor time. And based on taking once a cycle, you get what the slope is, and then you go ahead to do the rest of the question, to get the rest of the problems. Cruz,
I got that, sir. You are here to address the reason why why it's possible for us to have just a straight line in a build-up plot.
Okay. So let me answer that question. Okay, sorry about that. Now, first of all, there are no straight lines in life. These straight lines, they don't occur in life. They'll be a little staggered. But, and Cruz, think about it. So one question is, what can we do to minimize well-bore storage effects? And one is if you use a downhole choke. If you remember my discussion about well-bore effects, I talked about surface chokes and downhole chokes. Well-bore storage is actually fluid stored in your string, whether it is in the test string or in the annulus, which is impacting on your test results. So if you can cut off well-bore storage by using a downhole choke, this distortion will be greatly minimized. Second thing is if you were able to, if you drilled the well and then the well was well cleaned up, that you have minimal damage, this distortion will be minimal. But the straight lines you see in books are idealized situations. Remember when the test results I showed you mentioned that due to some constraints, they were not able to test to get boundaries. So for that report, you wouldn't have here. You had just had something like this. But most test results would have this portion, except I give you a question and then the early time is truncated from the result, from the test, from the data. Then you will have a straight line. That is just to make the candidate's life easy.
I got it, sir. Thank you, sir.